Pre-calculus 114, even and odd functions. And before we get into even and odd and why we name them the way we do, we want to make sure that you understand the premise of symmetry. So we'll talk about it a little bit. The first thing is make sure you understand that when you rotate, it's around a point, and when you are reflecting, it's over a line. So as we look at this, there's really only two things we're looking at. So for f of x, if you look, this is a reflective, and it's over, whoops, it's over the y-axis, or you could say the vertical line x equals 0, or y-axis. Those are the same thing. And you can verify because the points are on opposite sides the same length away. So 2 units away from the y-axis, 2 units away on the y-axis, 4 units away, 4 units away. Now as we look at g of x, this time we're looking at rotational. And it's around the origin, or you can give me the ordered pair 0, 0. And it's a combination of being like right 2, up 2, as this one's left 2, down 2. Okay, and then right 4, up 3, left 4, down 3. So they do have to have the same like heights as, and we'll talk more about this on the next slide. As you look at the next one, I guess I should really emphasize the point. H of x is the same thing as g of x, obviously with different points, but it is still rotational around the origin. Save me some time, I'm just going to write 0, 0. As we move down for p of x now, is it around the origin, or is it a reflective over the y-axis? It's a reflection over the y-axis. I just like writing it in terms of x equals. And again, you can see, okay, well, if it's on the y-axis, I guess I didn't give you the dashed line like I was supposed to. If the point is on the y-axis, then it's 0 points away. That's why its point of reflection is itself. And then the point of reflection of 1 unit away is 1 unit to the left. 2 units on the left, it needs to match up with 2 units on the right, and so on and so forth. Here's another rotational around the origin, 0, 0, and then there's one more reflective. And again, it's over the y-axis, but again, I just prefer writing x equals 0. I'm good either way. So what we're going to do is investigate this a little bit further. You can read these notes on your piece of paper, or pause and read it on the slide, and I'm going to move on to the next. So what you're supposed to realize is there's y-axis reflective symmetry for the functions f, p, and q. Oops, I hit the wrong button. So we're looking at f, p, and q. And all I want you to do on this slide is match up what points match up with which ones. Now, what some people would do is just list out all the points of f, but I want to actually point out like -4, 1 when it's reflected maps onto the point 4, 1. So instead of just giving you a list, I want you to realize that -4, 1 and 4, 1 match for a reason. And then same thing goes for the next point, which I already forgot what it was, -2, -1. Maps onto the point that would be +2, -1. And I'm also going to point out the one that doesn't look like it maps onto anything, which is that 0, -3. It does technically map onto another point, but it's actually mapping onto itself. So I wrote a little bit more here, but there's something significant that I want you to investigate, is what's unique about these values as we're looking at the ones that map to each other. And do you think that's going to be a common pattern for all y-axis reflexive problems? So let's look at P of x and see if it matches. So P of x right here, where we have negative 5, 4, is being mapped to 5, 4. I don't like that this magically changes colors, but we'll be fine. That's a comma right there. And then the other point, negative 3, negative 5. Maps with the reflection to 3, negative 5. And there's just a few more. Negative 2, 0. Would be mapped onto 2, 0. They also give you negative 1, 3. If I remember correctly, gets mapped onto 1, 3. And then something we've already discussed is that 0, 4, even though it's only written once, technically maps onto itself. And then we want to investigate Q of x, and we're answering the same question. Is there a pattern going from negative 5, 4 to 5, 4, negative 3, 0 to 3, 0? And so on and so forth. And I think by now you've probably already figured out what the rule is for this y-axis reflective symmetry. And basically what it boils down to about the y-axis reflective symmetry is that if you have a negative x and the y value stays the same, it's going to map onto the positive x and the y value stays the same. Now, y could be negative in this problem, just so you know, and same thing with x. Now, the way we typically write this is in function notation. So what you'll see is we sort of write it like this, that f of x, if x is positive, I know I'm writing it backwards right here, and remember f of x is y, all right? And if I want to compare it to f of negative x, remember this is the y value of this. So maybe I should highlight to emphasize. This is the y value of this one. And then just change colors. This is the y value of this one. But what do you notice about the y's between the two problems is they're the same. They are equal to each other. And there it goes changing the color back to the other one. They are equal to each other. So I'm going to share the answer key with you shortly, but this is the main thing to look for y-axis reflective symmetry. Now before I share that answer key, let's look at the origin rotational symmetries. So the origin rotational, well, what functions had the rotational with the origin? That was G, H, and R. And we want to look at what parts mapped onto the other. So I pointed out, oops, I want to start with G. I'm going to start with negative 4, negative 3. So negative 4, negative 3 mapped onto positive 4, positive 3. And then I already forgot what the next one. I think it was negative 2, negative 2. Please double check. Mapped onto positive 2, positive 2. And then the last one, which was only there once, was 0, 0, does technically get mapped to itself, 0, 0. So let me double check that I did everything. Yep, right there. And you want to say the same thing about h of x, how negative 3, negative 4 map to 3, negative 4, mapped onto positive 3, positive 4. I think it was negative 2, negative 1 was the next point. So before moving on to R of x, what do you notice about each of these mappings? So we can go back to a highlighter, maybe go back to just a different color. Is what do you notice about this x to this x, and this y to this y, this x to this x, and this y to this y? And I could go on, but hopefully you're noticing a pattern. And at any point you want to pause the video and soak it in, that's fine with me. But as we look at R of x, the reason why I would like to look at R of x is, does the origin even have to be included for it to be rotational? Oops, I didn't even put that point on there earlier. It does not have to be included to be able to say, oh, well, negative 5, 4 mapped to 5, negative 4. So this was negative 5, 4 mapped to 5, negative 4. I already forgot the next point. Negative 2, 0. Sorry, negative 3, 0 to 3, 0. And then negative 1, negative 2. And then that one was mapped to 1, 2. Now, I do want to point out, because some students will get this confused when they look at the zeros not changing signs. Well, 0 is not technically positive or negative. So that's why, if anybody's stopping there and saying, oh, well, that breaks our rule. Well, no, it doesn't, because 0 isn't positive or negative. So what's the mapping that we're looking at? Is, and that, again, I apologize. I sort of wrote this one backwards. Most people would start with the positive ones. But what do you notice about every one of these is that they change signs for both. So negative x, negative y. So how we typically see this written, and now I'm thinking about it, I actually think I wrote that one backwards, but that's okay. So I'll write this one backwards as well. Is sometimes what we'll write is, so this function would be f of x is equal to, now as a reminder, so I'm not trying to confuse you, that f of x is the y value for x. So what is f of negative x? We also have to change the sign of y. So that's why there's a negative, I think it changed colors on me again, negative of this. Because as a reminder, change colors again, this y is the same as saying this. So as we look at rotational symmetries, what it's saying is you better change the sign of both the x and the y. So this is going to be our test moving forward. And as I promised, I'm going to share the answer key with you. And this person, for the answer key, shares it more in words as an observation than the way I wrote it. But I'm trying to get you to be a better math thinker than this. So go ahead and pause the video and write down anything. Read it, soak it in. And I'm going to share the top of the next one because I only have a minute left. Top of the next page. And I just prefer function notation. So this is the numerical definition of what it means to be an even function. So from this point forward, I hope that when I say that something is an even function, you know that that means that you change the x value to the negative, but the y value stays the same. And graphically, it is a y-axis reflection. Likewise, with an odd function, if I ever talk about an odd function, I hope you realize that you change both signs of x and y, and graphically it's a rotation around the origin. So go ahead and pause the video. Write down anything you need to.